Okay, so before we actually start looking at some past paper questions on circle theorems, I think it's worth spending a few minutes, first of all, familiarising ourselves with the language that's used in the circle theorems, then look at how they are formed on circles, and once we've got our heads around that and we can spot them, then we'll take a look at some past paper questions. So I'm assuming you're higher tier, so you already know the common vocab associated with circles. So I'm talking about diameter, which would be right the way across through the centre, radius from the centre to circumference, circumference, which is the distance all the way around the outside. So I'm taking those as given, but these ones you may be less familiar with. So the arc on a circle would be, if we had 2 points on the circle, let's say we had a point there A and a point over here B, then an arc of the circle would be the part of the circumference that joins those 2 points. So there are 2 arcs. There's the smaller one going in this direction, or there's the larger one which is in this direction. And usually with the larger and smaller bits of circles, we refer to them as minor and major. So that would be the minor arc AB, and that would be the major arc AB. So the arc AB is the distance around, so if I try and colour that in blue, that part there would be the minor arc. A chord would be a straight line that joins 2 points on a circle. So if I'm keeping with the 2 points AB and I join those, that would be a chord. Joins 2 points. So here I've got my arc, there I've got my chord. This would be minor arc. And then a segment is the region that is divided in the circle by that chord. So we've got 2 segments in the circle. We've got this one, the minor segment. So this region here would be in minor segment, and what's left up there would be a major segment. So that's arc, chord and segment. Arc is part of the circumference. Chord is a line that joins 2 points on the circumference, and the segments are what the region of the circle is divided into when it's cut by a chord. And then 2 other words that we need to know what they mean. Tangent are used in circle theorems, and tangent is a line that just touches the circumference of a circle but does not cut the circumference. So if it cuts it, it's a chord. If it touches it, that's a tangent. So tangent only touches the surface, the circumference. And a sector, what sector does is it cuts a slice out of your circle. So it joins the centre, so it's the intersection of 2 radii. That would be the smaller sector, so the minor sector, and the big bit that's left would be the major sector. So sectors are, the word sector isn't used when we're talking about circle theorems, but all the other terms there, arc, chord, segment and tangent, we will be meeting when we look at these circle theorems. Okay, so let's take a look at the language and how these things are then made up. So the first one, the angle subtended at the centre of a circle is twice the angle subtended at the circumference. Now what that means is if you take 2 points on the circumference of your circle and you fire them up at the circumference anywhere, So if it fires up to the circumference and then from the circumference back to the other point, that angle is directly related to the angle if you're coming from the same points on the circumference and the relationship is that angle is half that angle, or that angle is twice that angle. So that angle, if that angle is x, this angle is double it. So if that angle is 20, that angle is 40. If that angle is 60, that angle is 120. If this angle is 140, this angle is 70, and so on. And it doesn't matter where you come from. Okay, so if I move the points, it's a different pair of points firing to the circumference. If I fire that to, oh, smudged. The fire to the circumference, fire to the center, whatever that is. So if that is y, this angle here is 2y. So it tends to be thought of as an arrowhead. Okay, so sometimes called the arrowhead theorem because of the way that that is drawn. But it doesn't always have to look like that. If you consider our points, so if I start with a point there A and a point there B, if I fire this way to the circumference, okay, so it's going to circumference, and here it goes to the center. Okay, then again, the angle at the circumference, the angle at the center, is twice the angle at the circumference. So this time, these are the related angles. If that's angle Z, then that's angle 2Z. So it doesn't always look like an arrow. If the angle at the circumference is obtuse, if it's greater than 90 degrees, then it's going to look more like that one there. But it's the same theorem. Angle at the subtended at the center of the circle is twice the angle subtended at the circumference. Okay, so the next one that we need to know about, angles subtended by an arc in the same segment of the circle are equal. So angles subtended by an arc in the same segment of the circle are equal. So what that means, again, if we take 2 points A and B, there is our arc. Okay, now if we think that if we throw a chord across there to create segments, okay, that gives me 2 segments. So what this is saying is if I fire to this arc anywhere in this arc and back to the other point, it doesn't matter where it hits the circumference, it will always have the same angle. So that angle there is going to be exactly the same as an angle that's firing hitting and bouncing there, same angle, which would be the same as if I fired one over here. So that again, each of those is the same angle, so it doesn't matter where it's hitting the circumference, it's going to be the same size. And exactly the same would happen if I fired it in the opposite direction. So if it came down this way, so I'm working in the minor arc, that angle there is different to those ones up there, but it'll be the same as any other angle I fire within that segment. So two little loops around that just to show that it's different. So if I fire another one to there, that is going to be the same. So that's angle subtended by an arc in the same segment. Now, a cyclic quadrilateral is a four-sided shape where the 4 points, the 4 corners of the quadrilateral form or lie on the circumference of the circle. So if I put one there, one there, one there, and one there, and join those up, okay, so there's nothing regular about that quadrilateral. None of the sides are the same length, none of the angles are equal, but the property is that they're opposite angles. So that angle there and that angle there, if I call that X and Y, then those two add up to 180. And then because the other property of any quadrilateral is that all the angles up to 360, the other opposite sides must be equal as well. So if I call that A and B, A and B also add up to 180. So that's a property that only happens if the quadrilateral lies on the circumference of a circle. Okay, this is one of the easiest ones to spot, which is if you have a semicircle, so if you have a diameter or chord that goes through the center of the circle, any angle generated by firing off one end of the diameter, hitting the circumference and bouncing back, wherever that happens, the angle is 90 degrees. So we'll just draw a couple of those to just make sure that it looks about right, because I'm not measuring any of these. So if we fire to there and now bounce back to the other end of the diameter, that's a right angle. And if I fire further over, that is also a right angle. And if I fire further over again, it still remains a right angle. So that's usually a nice easy one to spot, and obviously it would be exactly the same if it was in the other half of the circle. Okay, this is another nice one to spot, which is the angle between a tangent and the radius drawn to the point of contact is 90 degrees. So regardless of where I draw my tangent, so I draw a tangent there, where the tangent joins a radius, like there, I'm going to have a 90-degree angle. If I draw my tangent somewhere else, where the tangent joins the radius, I'm going to have a right angle. So the angle between a tangent and the radius drawn to the point of contact is 90 degrees. And then we've got two more to look at. Not to be able to spot, unfortunately. From any point outside a circle, just two tangents may be drawn, and they are of equal length. So if I choose a point, from that point there are only two tangents I can draw. So for example, that's not a tangent, so you're looking for the tangent, so that looks tangenty. So there's one, and there's only one other tangent that I can draw from that point, which will be there, and the distance between the point and the tangent and the point and the tangent will be the same, which means if you then join that up with the radius, if you join up the two tangents, what you will have is an isosceles triangle. So if there are my two tangents, the distance from there to there and the distance from there to there are going to be the same. And then similarly, if you then do join your tangents to the center and join the tangents to the center, and you know that you've got right angles there and there, what you can also do is divide that up into two right angle triangles which are identical. And quite often you'll see that on an exam question. So it's testing two things really. It's testing your knowledge that those are equal lengths. It's testing your knowledge that that's a right angle. So it's giving you two identical right angle triangles like that. And then the final theorem is the hardest one to explain really, or to translate from the way that it's written. So luckily it's given a name of its own, so you haven't got to write the whole thing out. It's called the alternate segment theorem. So let's see if I can draw this now. Okay, so the angle between a tangent and a chord through the point of contact, so let's draw ourselves a tangent, and a chord through the point of contact. So that means I'm going to create a chord, and one of the points on the chord is going to be the point of contact where the tangent cuts the touches the circumference. So I'll draw it over there. Doesn't have to be, but that's, so there's my chord. Okay, so the angle between a tangent and a chord, so there's my angle between my tangent and my chord, is equal to the angle subtended by the chord in the alternate segment. So what that means now, this angle is in this segment. If I fire this point anywhere onto that circumference and back again, okay, so we're going to go from there, doesn't matter where, up there and back to that point, that angle is equal to the angle subtended by the chord in the alternate segment. So that is equal to that. So if that is x, that is also x in there. And then the same thing happens the other side. If my chord, my blue chord, starts there, the angle between the tangent and the chord, so if I call that y, there's my chord, is equal to the angle subtended the other way, so that is equal to that there. So I mean, the way that I kind of got around that myself when I was a student was it's a bit like your Z angle but flipped. So it looks a little bit like a Z, but it doesn't go X the same, it doesn't go Y the same, it flips over. So that one there there's your Z, fires there and back again. There's your Z, fires there and back again. So it's a bit of a weird one to get your head around, but actually once you spot it, it's not that difficult to see. Now the biggest pain when you're looking at the past paper questions is that it's not enough to just work out the missing angles. They actually ask you to give reasons why those are. With this one it's easy because you can just write alternate segment theorem. With the others, they haven't got a name like that and you've got to somehow describe. Anyway, we'll take a look now in the next video clip at some of those.